Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 18, 2026, just about 4 days ago. It presents a comprehensive roadmap for shifting AI development from static models to what the authors call agentic reasoning, effectively turning large language models into autonomous agents that can plan, act, and evolve in dynamic environments. The paper is titled Agentic Reasoning for Large Language Models. And as we'll see later, the framework they propose covers everything from single-agent tool use to complex multi-agent collaboration, with some really significant implications for the next generation of AI systems. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 maps out this entire ecosystem, effectively serving as a visual table of contents for the paper. At the very top, it highlights the core paradigm shift, moving from static, passive inputs to dynamic, interactive contexts where models evolve over time. The diagram then splits the methodology into 3 key layers. First, the orange panel details foundational agentic reasoning, which gives agents the ability to plan, use tools, and search the web. Next, the blue panel shows self-evolving agentic reasoning, where agents use feedback loops and memory to actually learn from their mistakes. And finally, the purple panel covers collective multi-agent reasoning, illustrating how multiple agents can be assigned roles to collaborate on shared goals. Well, Table 1 breaks down this shift in detail, contrasting traditional capabilities with the new agentic approach across several dimensions. If we focus on the paradigm row, we see the fundamental change from passive, static input processing to interactive, dynamic contexts. Moving down to computation, the difference becomes even clearer because agents replace single-pass inference with multi-step reasoning that incorporates feedback. The table also highlights how statefulness evolves, moving beyond a temporary context window to persistent external memory. Finally, the learning and goal orientation sections show that while standard models rely on fixed pre-training, agents aim for continual self-improvement and explicit planning. So, Figure 2 zooms in on the specific mechanisms for planning reasoning, distinguishing between strategies applied at runtime versus those learned during training. On the left, the large blue section covers in-context planning, which happens on the fly without changing the model's weights. This area highlights workflow design, where agents follow structured steps, like perception and verification, and tree search methods that explore multiple future paths before acting. Then, on the far right, the green section shifts to post-training planning, focusing on reward design to permanently optimize agent behaviors. Alright, Figure 5 shifts our focus from planning to self-improvement, illustrating 3 ways agents process feedback. The first panel, reflective feedback, shows the agent updating its reasoning trajectory in real time, essentially critiquing its own thoughts during inference. Moving to the center, parametric adaptation represents a deeper level of learning where feedback actually updates the model's parameters, storing lessons permanently. Then, on the right, validator-driven feedback depicts a simpler loop, where external signals, like a failed attempt, prompt the agent to adjust its output and try again. Okay, having seen how single agents improve, Figure 9 expands the scope to agentic collaboration, showing how multiple agents work together. The blue panel on the left illustrates in-context collaboration, which organizes teams without retraining the models. This includes fixed structures like cascading chains or hierarchical setups, and even automated methods where an LLM orchestrates the workflow dynamically. Then, the green panel on the right details post-training collaboration, which permanently optimizes how agents interact. This involves advanced strategies like graph-based optimization to model communication pathways, or policy-based optimization to learn the best agent for each specific task. Moving from theory to practice, Figure 11 maps the reasoning framework onto real-world applications. The top section recaps the 3 layers we've discussed: foundational capabilities like tool use, self-evolving loops with memory, and collective multi-agent systems. The bottom row then shows how these apply across 5 distinct domains. For instance, in scientific discovery, agents might use planning to design experiments. In embodied agents, or robotics, they need real-time feedback to navigate physical spaces. The diagram also highlights applications in healthcare and web exploration, demonstrating that each field requires a specific mix of these agentic reasoning skills. Wrapping up, the key takeaway is the shift from static prediction to active, autonomous agents that plan and learn. This evolution from simple chatbots to systems capable of long-horizon reasoning is essential for real-world deployment, though it brings major challenges in safety and governance. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.